Now we'll talk about harmonics. Many musical instruments rely on standing wave patterns to produce sounds that are pleasing to the human ear. Whether it is a violin string or the air column enclosed within a flute, the vibrating medium, i.e. the string or air, vibrates in such a way that a standing wave pattern results. Each natural frequency that an object or instrument produces has its own characteristic vibrational mode or standing wave pattern. These patterns are only created within the object or instrument at specific frequencies of vibration. These frequencies are known as the harmonic frequencies, or simply harmonics. So, harmonics are a set of frequencies that arise from standing waves formed because of the physical properties of a particular system. At any other frequency other than a harmonic frequency, the resulting disturbance in the medium is irregular and non-repeating, so therefore we don't get a standing wave pattern. For musical instruments and other objects to vibrate in a regular periodic fashion, harmonic frequencies are related to each other by simple whole numbers, and we'll show this in a moment. We will look at two special cases of harmonics. First, a system with two fixed ends. This could be a string held at two ends or a closed tube of air. And the second is a system with a tube open at one end. This is important when we examine the physics of the human ear. But before looking at these systems, let's define some of the words and ideas that we'll need. So if we draw here a tube closed at both ends, or a system fixed at both ends, and we can draw a wave pattern, we can see we have points where the standing wave isn't moving, and these are nodes. When we have a maximum amplitude, this is called an antinode. The length of our system is defined as the length L. This can be of the pipe, tube, string, etc. And for aspects of this work, we also need to remember the relationship between wavelength, frequency, and velocity, which of course is V equals F lambda. In harmonics, we often refer to the nth harmonic, and by nth we could mean first, second, third, etc. N is always an integer number, i.e. you never refer to the half harmonic. N has to be a whole number. Now the example of a closed tube or a string fixed at both ends. We'll do the first harmonic to begin with. This is sometimes called the fundamental harmonic, and this is when we have n equals 1. So let's draw the waveform here, and we've got nodes that are fixed at both ends. Because we've got a closed or fixed, we have to have a point at both ends that's not moving. This defines the system. So if we want to work out what the wavelength is, we can see that we're only drawn half of the system. So our wavelength is twice the length of our tube. So lambda equals 2L for the first harmonic. Now to the second harmonic. This time we can draw a pattern like this. Here are our nodes. This is what the wave would look like if it was oscillating in the other direction. And this is n equals 2. And we can immediately see that our wavelength is equal to L. Now our third harmonic, n equals 3, we can draw the wave, and we've got n equals 3, and we can see that lambda equals 2/3 L. We can generalize this relation for a system with closed or fixed ends. We can say that lambda n equals 2L on n, where n is an integer number, 1, 2, 3, etc. We can also, of course, have a relationship between the frequency. Because we understand the wavelength, we can also put in the frequency, and this would have a component of the velocity in it as well. So Fn equals Nv on 2L. Now our harmonics example of an open-ended tube. So this time our system has one end fixed, so we have a node on the right here, so we always have to have that point still. But on the other side, we will always have an antinode, a maximum amplitude. This defines what waves we can fit into this system. We'll have the first harmonic, n equals 1, and we can draw the wave pattern. It's a little bit harder to see here, but the wavelength is 4 times the length, so lambda equals 4L. I don't have room to draw the entire wavelength. The second harmonic, this is not going to fit in this system because of our constraints of one fixed end and one open end. so we have to skip it and go to the third harmonic. Here n equals 3, we can draw it as such, and lambda equals 4 on 3 L. Again, we can't draw the fourth harmonic because that would require both ends to be fixed, which they're not. So we go on to the fifth harmonic, n equals 5, and we can see that lambda equals 4 on 5 L. So let's generalize this. So for a one open, one fixed or closed end system, the harmonics lambda n equal 4L on n, where n is only an odd integer. So we can't have n equals 2 in the system of a tube open one end and close one end. We can extend that to the frequency, Fn equals Vn on 4L.